Yeah, a level curve is a general concept referring to any taking a two-dimensional function, sorry, a two-variable function, i.e. a three-dimensional surface, setting the height of that function equal to some constant, and asking for all combinations of the input variables that give you that height. That would be a level curve. Isoquant is specifically terminology used for production functions in economics. Like isotherm, also a level curve is specifically for temperature. Okay? Okay. Okay, good. So that's multivariate functions. How do we optimize multivariate functions? Well, how did we optimize the univariate functions? Anybody remember? Well, so you have to find the derivative, set that equal to 0, and then you have to solve that equation. It may involve looking for two roots if it happens to be a quadratic function. It may involve looking for more roots if it's a higher order function. Probably not in most of the toy examples we will do in class. But in real world applications, you generally will have many more roots, but you won't have to do them by hand. You'll be able to use MATLAB or something like that, or an equation solver. Okay, so when we have multivariate functions, the process is exactly the same. We're going to be looking for a combination of input variables such that the slope of the function is equal to 0. But now, because we have multiple variables, the derivative is just a slightly more complicated beast than it was before. In the case of a univariate function, the derivative was just the slope of that function, or a function that gives you the slope for different values of x. Okay. Now, what's the analog of the derivative in the case of a multivariate function? It's called a partial derivative. Okay. Now, the partial derivative you can think of, this is why I drew the cross section here. The partial derivative is simply the slope of an analog function holding a bunch of input variables constant. Okay, so if you're looking for the partial derivative with respect to labor in that yield function I talked about, you hold fertilizer input constant, you'll be able to draw a, sorry, actually I switched the variables on you. This is holding labor constant. So if I hold labor constant, I can draw a cross section for how yield changes as I change z. This cross section function obviously has an ordinary derivative. This is just a function of one variable z. So you could take, let's call f y as a function of z given that b is equal to 2. You could take f prime with respect to z to be the slope of this function. And this f prime is just what we call the partial derivative with respect to z. Okay? That is how the slope of the function, what is the slope of the function as you change z while holding constant b. Okay? And you would have the analog definition if you were looking for the partial derivative with respect to b. Okay, so and so here's the formal definition. the partial derivative of xy with respect to x, it's written this way, sort of a squiggly d, is the derivative of the function where y is treated as a constant, i.e. y is given at some constant value, and f is considered as if it were a function of x alone. Okay, so that's exactly what this is. Okay, hold all other variables constant and change just the one variable with respect to which you're taking the partial derivative. And this logic applies if the function is a function of more than two variables. The partial derivative, by definition, is always with respect to a single variable, holding all others constant. Okay. Okay. So what's the interpretation of the partial derivative? Well, it is simply the rate of change of the function with respect to x for all other variables held constant, for all other input variables held constant, right? Or keeping all other input variables constant, what is the what's the change in the output variable for a small change in x, when x is the variable with respect to which you are taking the partial derivative. Okay. So how do you do partial differentiation? Well, the mechanics are very simple. Since we assume that all other, by definition, the partial derivative assumes that all other variables are kept constant, you can treat all other variables as a constant, and as such, their derivative would be 0. So take, for example, this function, 5x cubed y squared, and you want to find the partial derivative with respect to x. Okay. You could think of this function as a function simply of x with this y squared as part of the constant. Okay, so here I've written it as if 5y squared is some constant times x cubed. Okay. Well, if you had some constant times x cubed and you had to take, and it was just a univariate function of x, then what would be its derivative? 3x squared times the constant. Okay, so that's what you have, 3x squared times the constant. So don't forget the constant, right? Okay. Similarly, here you have a slightly more complicated function. This is a function of x and y inside the brackets to the power 8. Okay. So you could simply think of this as 4x, that's the function of x, plus 3y minus 5, that's some constant, raised to the power 8. Okay, so it's as if f is really 4x plus some constant raised to the power 8. Okay, this is f of x. So f prime of x here would be what? 8. Okay, something in there to the power 7. Okay, so that's going to be 4x plus c. Am I done? Times 4, right? Plus the inside derivative. So I could just multiply here by 4. Okay? And you would be just fine. So that's 4 times 8. is 32. Okay, and that's what you have here, except that you know this c is really 3y minus 5. Okay? Yeah, so this c, I just defined this constant on the fly, meaning when I look at this expression, this is a function of x and y. However, I'm looking for the partial derivative with respect only to x. In other words, I'm taking a cross-section of that function holding y constant. Since I'm holding y constant, I can pretend this is really a constant, and this I know is a constant. So on the fly, I defined c to be this constant. It just made it simpler so that when I took the derivative, it was easier. Okay? Everybody good? Okay, so let's look at that heat loss problem again. We've got the heat loss function that we worked out before as a function of x, y, and z. So let's say we have to calculate and interpret the partial derivative with respect to x, that was the length of the building, if the current dimensions of the building are 10, 7, and 5. Length 10, width 7, and height 5. Well, what's the partial of this with respect to x? What's the partial with respect to x of this first term? 11y. What about this one? What's the partial with respect to x of this second term? 0, right? This is, we would treat y and z as constants. And the last one would be 15z. Okay, so this is 11y plus 15z. And you could evaluate that at the value 10, 7, 5. It's only a function y and z, so we only use the 7 and 5. It gives you the number 152. Well, what's the interpretation of 152? I have the answer up there, but maybe somebody can read it to us. But if the length of the building is increased by 1 unit, right? So if I go from a length of 10 meters, I guess this was in feet, right? 10 feet to 11 feet, then the rate of heat loss for the building as a whole would increase by 152 units. Yes, absolutely. Partial derivative could be negative. In this case, it wouldn't be because heat loss is going to be increasing as you increase the dimensions of the building. But there's no, for example, in the case of the fertilizer and labor, if you already had passed the optimal level of labor and fertilizer and you added more labor, you would have a negative partial derivative. Okay? Okay, but now suppose that we want to find the dimensions of the building that minimizes heat loss. Okay? As with univariate optimization, we're going to look for critical points of the multivariate function, and those critical points will be combinations of the input variables such that the partial derivatives are equal to 0. Okay? Now, there are, to look for a minimum or a maximum, there is a first order condition and a second order condition. When we optimized the univariate functions, I didn't tell you what the second order condition was because I built it into my description. I told you that if you have a concave function and you look for a zero of the ordinary derivative, then you are at a maximum. If you have a convex function and you look for a zero of the ordinary derivative, then you're at a minimum. Okay? The first order condition is a necessary but not sufficient condition for attaining a minimum or maximum. Okay? That first order condition is that the derivative is equal to 0. If you want a sufficient condition as well as a necessary condition, then you have to look at the second order condition. In the univariate case, we didn't bother with that because we simply said that you'll either be looking at convex functions or concave functions. And if you're dealing with a concave function, you're going to have a maximum. And if you're dealing with a convex function, you're going to have a minimum. Okay? And you can remember that by remembering the shapes of those graphs that I put up right at the beginning of this session. With multivariate functions, you typically need to think about second order conditions more carefully because there are many more possible scenarios. It's not so much that the function is concave or convex because you're in 3 dimensions now. It could be concave if you take a section along one axis, but convex if you take a section along the other. It could be concave in both ways, and so on, right? And if you have three input variables, then you're in even more, with even many more probabilities, many more combinations. So you would need to look at the second order condition. Okay, so we'll talk about the second order condition in a second. The first order condition is always that the partial derivatives of both with respect to x and with respect to y are equal to 0. And of course, if this were a function of 3 variables, then all 3 partials would have to be equal to 0, and so on. Okay? For the energy loss, the heat loss function, we have a function of 3 variables. If we're looking for a minimum of this function, then we would have to set all 3 partials equal to 0. Okay? Now here, suppose that we want to design the rectangular building with a specific volume. Of course, if your building is very small, then its heat loss will be much less than a large building. The key here is to have minimal heat loss for a particular size. So let's suppose that we've set the volume equal to this. I've chosen this number so that its root is an integer. So we don't have to, so we can do things nicely. Okay, we have to minimize the heat loss function such that the volume, which is of course x times y times z, is that number. Okay? Oh, ST means such that. Such that. You'll see this a lot. Okay, good question. Okay, so we have to minimize that function. Well, actually, this it simplifies things a little bit because we have a constraint on the potential combinations of x, y, and z. And that's going to allow us to eliminate one of the variables. So instead of a 3-dimensional problem, we'll have a 2-dimensional problem. Okay, so x, y, z has to be this. So suppose that we just call the constant v this number. So that's going to just reduce the ugliness of the algebra. We can express z in terms of x and y and v. Okay, so that's just dividing v by x times y. Okay, and then we can substitute for z in the original heat loss equation. So it's going to be 11xy plus 14y, substituting for z here, plus 15x, substituting for z here, and I get this equation, right? Okay. Okay, so to minimize this function, we're going to compute partial derivatives with respect to x and y, equate them to 0, and find the values of x and y which satisfy those two equations. Okay, so this is my heat loss function as a function of x, y, and v. But v is just a constant, so there are no partial derivatives for that. Okay, so you know how to take this partial derivative. With respect to x, that's just 11y. And here, with respect to x, is 14v over x squared. Okay, everybody know how to do that, right? And then do the same thing with respect to y. That's going to be 11x. There's no y in that term, so that's 0. And here there's a y, so it's 15v over y squared. Okay, by the way, this is notice this minus sign here. Okay, everybody understand why there's a minus sign here? Tell me if you do not understand. Yes. Okay, so so that's that, right? So we had 14v over x is really 14v x to the minus 1. Okay, so when I take this derivative, I take the power and put it in front, make it a coefficient, and reduce the exponent by 1. So I'll get minus 1 times 14 v x minus 14v over x squared. Okay. So we worked out the partial derivatives. We set them equal to 0. Now we've got two equations in terms of x, y, and v. We know what v is. That's just a constant. So we can solve. We have these two equations. Y is expressed in terms of v and x, so you could just substitute for y in here. And if you do that and a bit of algebra, you get x, or x cubed, in terms of v, which we know what that is. And v, this number was chosen so that x turns out to be an integer. Okay. So you know that x would be 56, and then once you know what x is, you can work out y and z. Okay, so the building which minimizes heat loss and has volume equal to that has to be 56 feet by 60 feet by 44 feet. Okay, so that shape is, of course, a function of the particular geography of that building, right? So it would change for a different geography. Let's talk briefly about that second order condition. Because we are dealing with now a three-dimensional surface, here is what we call a saddle point. This is a place where along one section, if I were to cut a section this way, the function, the cross-sectional function, would look concave. And if I were to cut a section this way, the cross-sectional function would look convex. So at this red point here, my partial derivative with respect to this axis would be 0, and the partial derivative with respect to this axis would be 0 too, but I'm neither at a maximum or minimum of that function. If I go a little bit this way, I could go higher. If I go a little bit this way, I could go lower. Okay, so I am at a critical point of the function. It's a saddle point. Okay, so to avoid these kinds of, avoid finding points like this when we simply set the partials equal to 0, you'd need to look at the second order conditions. And most problems that I would give you would not involve that, but I do want you to understand that conceptually. And I've given you how to work out the second order conditions here. Okay, so you could, yes. Well, I'll tell you in a second what it has to satisfy, right? So if you, and this is just for two variables, there are analogs for larger numbers of variables. So for a function of two variables, f as a function of x and y, if the partials are equal to 0 at the point x star, y star, you can define this quantity. This is a function of the cross partials. This is the second derivative with respect to x times the second derivative with respect to y minus the cross partial. So this is, you take a derivative of the function with respect to x, and then you take a derivative of that derivative with respect to y. So it's called the second order cross partial.
Could you run through that again?
Yeah. You take, so let's say that you have a function of x and y. You take a derivative with respect to x. Okay. Let's just call that g. That's also a function of x and y. And then you take a derivative of g with respect to y. Okay? That's what I've put up there as okay? If you think of a hill and you're trying to work out how high you would go if you move in a certain direction, doesn't matter whether you go east and then north or west, north and then east. Okay?